We are now moving to Module 13, which is radical expressions. So we're changing our vocabulary word completely. We're not dealing with fractions anymore. We're dealing with radical expressions. And the first thing you all have to remember is the word radical is interchangeable with the word root. And I would believe by now, in your experience in math, you've already heard about a square root before. So this whole chapter is going to be about roots. Well, first thing we have to know is and understand is where do roots come from? Roots come from a certain set of numbers. A root is an operation. A radical is an operation you do to a certain set of numbers. Like I said, the most famous root you probably heard of is square root. Well, you can only square root certain numbers. And those numbers that you could square root have a name. They are called perfect squares. So this whole chapter is going to be based on certain sets of numbers, which are very important. So the first thing we're going to do today is we're going to list out what numbers are perfect squares. So let's go to the board. A perfect square is a number times itself, and you've already seen this list when we were doing factoring. Remember the rule factoring difference of perfect squares? Well, we had to know that set of numbers. A perfect square is a number times itself, so we're going to make that list again. So we're going to start out. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. So I'm going to continue the list. So this would be 16, 25, 36, 49, 64, 81, 100. That's the first 10 perfect squares. But for our work in this chapter, we need to go a little bit higher. We're going to list the first 20. So 11 times 11 is 121. 12 times 12 is 144. Then it goes 169, 196, 225, 256, 289, 324, 361. 20 times 20 is 400. And then I'm going to put a ... just to indicate that that list can go on forever. But as far as our work in the chapter, we're going to work with the first 20 perfect squares. Now, the reason why these are called perfect squares is they can all be rewritten with exponents of 2. For example, I could take 9, and we know that was 3 times 3. And 3 times 3 is 3 squared. So what we're going to learn today is where does a square root even come from? You get roots from the opposite of doing exponents. And it all goes back to basic rules of arithmetic. You've heard me all semester say, please excuse my dear Aunt Sally. That's a way to remember order of operations. And every operation in math has something that will undo it. It's opposite. The opposite of adding 3 is subtracting 3. The opposite of multiplying by 3 would be to divide by 3. So guys, there's got to be an opposite to exponents, which is the P. But P doesn't just mean parentheses. It means a symbol. And there's lots of symbols we use in math. There are parentheses and brackets that both do the same thing. They mean multiplying. There's absolute value symbols, and then there are your root symbols. So we've got to learn if exponent is an operation you do to a number, then it has an opposite. And the opposite of exponents are radicals or roots. So up here, if you look, I wrote 3 squared. I know 3 squared is 9, which means I can then do the opposite. And the opposite of squaring would be do a square root. And that's how we would write the square root of 9. And that means the opposite of squaring. If squaring means multiply a number by itself, then that's what this root means. A root symbol, a radical symbol, does not mean division. It means a number times itself. So when I write the square root of 9, I'm asking you what number times itself gives me 9. And that answer is 3. So it's important that you understand roots come from the opposite of doing an exponent. The opposite of squaring is square root. So that means this list of numbers, these are all the numbers you could square root. None is on that list. If I ask you the square root of 9, there's no work. You tell me the answer. It's 3. So that's important. If you know this list, you could square root many numbers without doing any work. Okay, let's look at our notes. So if you go to our notes, let's look at our first set of examples. Okay, there's no work here. All of those numbers on those examples are on our list. So when I say square root of 1, I'm asking you in words, what times itself is 1? What would you say? 1. Square root of 25, what times itself is 25? 5. Square root of 64, what number times itself is 64? 8. Square root of 289. Now you're going to say, I don't know the answer to that. Yes, you do. If you just memorize the list, 289 is on the list. How do you know the answer? You count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That means 17 times 17 is 289. So what is the square root of 289? 17. Okay, if you look at the next example, I did not put 0 on the list, but that's common sense. What times itself is 0? 0. Okay, next one, square root of 16. What number times itself is 16? That's 4. Now let's go to the board and look at examples 7 and 8, because those are a little bit trickier. They do not look exactly alike, so they're not going to give the exact answer. 7 is asking negative square root of 16. 8 is asking square root of negative 16. If you follow, please excuse my dear Aunt Sally, you always work inside a symbol first. So we're going to do, what is the square root of 16? 16's on the list. It's 1, 2, 3, 4. So what number times itself is 16? That's 4. Now the negative comes down in front. What that negative means is you're multiplying negative 1 to 4, which is negative 4. So the square root of 16 is 4, but because there's a negative 1 in front, because that's invisible, understood negative 1, negative 1 times 4 is negative 4. Example 8 is totally different. I am square rooting the number negative 16. So first of all, you can't take that negative outside. That stays inside the symbol. I'm asking you, what number times itself is negative 16? Because that's the definition of square root. What number times itself is negative 16? Well, is it 4? Can't be. 4 times 4 is not a negative 16. Is the answer negative 4? It can't be. Negative 4 times itself, negative 4, is going to give you a positive 16. Remember, this symbol is a definition. You have to follow the definition. When I write this symbol, square root, I am asking you, a number times exactly the same number. Is there a number I can multiply twice that would give me negative 16? There is not. There is no number times itself that will equal negative 16. This can't be done. Even if you use a calculator, you'll get an error. Well, if it can't be done, we have no answer for it. The way you write no answer is you would write no real root. Okay, it's very important you use the correct vocabulary. Don't you tell me the word undefined here, because undefined is only dealing with fractions with denominators of zeros. We're not dealing with that here. Don't you tell me no solution. No solution tells me when I'm working an equation. This is not an equation. When you cannot do a square root, you say there is no real root. Real means a number on the number line. There is no number on the number line that if you multiply it to itself would give you this. You need to memorize, you can never square root a negative number. Never. The answer will always be no real root. Now, in your notes, let's look at examples 9 and 10. One has a fraction and one has a decimal. And a lot of people get scared of that. Don't be afraid. If you could square root a whole number, you could square root a fraction. To square root this fraction, this bar, this symbol means you are square rooting both the numerator and the denominator. 81 is a perfect square. It's on the list. 100 is a perfect square. It's on the list. There's no work here. What times itself is 81? 9. What times itself is 100? 10. So the square root of 81 over 100 is 9/10. The same thing with the decimal. I have 49 hundredths. If the decimal point wasn't there, that would be the number 49. 49 is on my list. So if 49 is a perfect square, then 49 hundredths is a perfect square decimal. We know the square root of 49 is 7, but we're doing it 49 hundredths. What decimal times itself is 49 hundredths? 7/10. So it's important This whole chapter is based on this list of numbers. If you know this list, you could square root. Now, unfortunately, squaring the exponent 2 is not the only exponent that exists in math. You all know exponents can be any size. So not only can we do a square root, we could do other roots. And that's what we have to keep discussing. So let's go and look at another root. So if you go to your notes, let's go to the operation cubing. Cubing means you're multiplying something 3 times. We've already seen this list when we did difference and sum of perfect cubes in factoring. So we're going to understand that if you can cube a number, you could do its opposite, cube root. Again, to do a cube root, you got to know what numbers are perfect cubes. So let's go to the board and list our numbers that are perfect cubes. So, what number we're going to multiply 3 times to give us a perfect cube? The first perfect cube, obviously, is the number 1. Because 1 times 1 times 1 is 1. The next perfect cube is 2 times 2 times 2, which is 8. 3 times 3 times 3, which is 27. 4 times 4 times 4, which is 64. 5 times 5 times 5, 125. 6 times 6 times 6, 216. 7 times 7 times 7, 343. 8 times 8 times 8, 512. 9 times 9 times 9, 729. 10 times 10 times 10, 1,000. These numbers could all be written with exponents of 3. For example, you all know 8 really is 2 times 2 times 2. We could write that as 2 cubed. Now, if that's an exponent of 3, it has an opposite. If I call that cubing, the opposite cannot be square root. The opposite would be a cube root. And the difference between a square root and a cube root is putting this little 3 there. When you put that index of 3, that means cube root. So if I wrote cube root of 8, I'm asking you, what number do you multiply 3 times to give you 8? And we know that's the number 2, because 2 times 2 times 2 was 8. So you can cube root any number that's a perfect cube. Therefore, by knowing this list, there's no work. So let's go to our examples in our notes. All right, so let's look. The cube root of 27, there's no work. What number do you multiply 3 times to give you 27? That's 3. The cube root of 64, there is no work. What number do you multiply 3 times to give you 64? That's 4. Cube root of 1. What number do you multiply 3 times to give you 1? That's 1. Now, everybody look very closely at example 6. That says cube root of -8. That is asking you what number can you multiply 3 times to give you -8. That has an answer. Let's go to the board. If I write cube root of -8, what number can you multiply 3 times to give you -8? That is the number -2. I will prove it to you. If you take -2 and multiply it to itself 3 times, that's what cubing means, 3 times. A negative times a negative is a positive. A positive times a negative is a negative. And 2 times 2 times 2 is 8. So you got to make a special note that cube roots, you can do a cube root of a negative number. You just can't do a square root of a negative number. So you got to pay close attention to the index. If it's cube roots, you can do a negative number. Now, here's our problem. Who says exponents are just size 2 and 3? Who says you can just square a number and cube a number? You can do any size exponent. Therefore, roots have no end. You could do a square root, a cube root, a 4th root, a 5th root, a 6th root, a 7th root, and on and on and on. The concept is the same. Roots means multiplying the same number so many times. Square root means to multiply a number 2 times. Cube root means to multiply the same number 3 times. So now let's look at our notes and look at some other roots. So if we go to our notes here, if you look at the indexes. They're 4s, 5s, and 6s. I'm asking you to do 4th roots, 5th roots, and 6th roots. Now that we don't got to make a huge list, we just got to understand the concept. The 4th root of 16 means what what number do I multiply 4 times that can give me 16? Well, could it be 1 times 1 times 1 times 1? Nope, that's a 1. But can it be 2 times 2 times 2 times 2? Sure it can. So the 4th root of 16 is 2. If you look at example 3, that is the 5th root of 1. What number can you multiply 5 times that makes 1? Well, that's obvious. That's a 1. If you look at example 5, that's the 6th root of 64. So let's go to the board and look at that. So even though I'm not going to make a list of all the numbers that you'd multiply 6 times, let's think about this. The sixth root of 64 means what number can I multiply 6 times to give me 64? You could either sit here all day and go 1 times 1 times 1 times 1 times 1 times 1, 2 times 2 times 2 times 2 times 2 times 2 till you get it. Or you can sit over here and do a factor trade. You can actually break this down and figure out what number multiplies 6 times to give you 64. So I know 64 is 8 times 8, but that's only 2 numbers. 6th root means I need 6 numbers. 8 is 2 and 4. 4 is 2 and 2. That's 3 numbers. 8 is 2 and 4. 4 is 2 and 2. Well, now it's obvious. If I take the number 2 and multiply it 6 times, I would get 64. So when I ask you this, the 6th root of 64, that's what I'm asking you. What number do you multiply 6 times that would give you 64? It is 2. Now, if you look at example 7, that says the 6th root of negative 64. Can you multiply the same number 6 times to get a negative 64? There's no way. Even if you put a negative out 6 times, a negative times a negative is a positive, a negative times a negative is a positive, a negative times a negative is a positive. There is no way to multiply a number 6 times to make a negative 64. So we say the answer is, if you can't do it, no real root. Okay, next video I see you on, we'll be doing this with algebra. Have a good day.